In this video, I try to show the solution of the problem of finding all nth primitive roots of unity. First of all, we'll briefly talk about complex numbers because the problem is about complex numbers. So a little bit about what they are, how to denote, multiply them. Then we will talk about roots of complex numbers and how they differ from roots of real numbers. Next part will be about what is a group in abstract algebra and the generator of the group. After that, we will combine these two seemingly different topics and we will be almost at the end. So let's start. The question has few layers to peel back in order to understand it. First, we have to talk a little bit about complex numbers. They are more, complex than reals. It's the expansion of real numbers, but not in the sense that real numbers were expansion of rational numbers. We haven't found a place on a real axis between reals to place their complex numbers, as we did with rational and real numbers. Instead of this, we add something like the second dimension. Real axis stays the same, is the horizontal line, and we add a vertical one and call it imaginary. Now we have a plane, complex plane. We choose a point. Let's say that the first coordinate is A and the second one is B. We will denote our number z as A plus IB, where I is some special character, but we don't care about it now. A plus IB is called the algebraic form. There's also another way of denoting our number. Instead of taking plane coordinates, we can consider the distance from the origin to the point and the angle between the real positive half-axis and line going through our point and the origin. Using Pythagorean theorem, we get the length, called modulus, and using some trigonometry, we get to know the angle. We will denote our number in a new form as r times e to the power of I phi, where r is the modulus and phi is the angle. It's called the exponential form. We call the plane on the right the polar plane. It's useful for visualization, complex numbers multiplication. It's more convenient to see how it works on a polar plane. If we want to multiply two complex numbers written in the exponential form, we multiply modulus and add the angles. If we want to square our number, we take the second power of modulus and multiply the angle by 2. Now we have to talk a little bit about roots of a complex number. The most important thing is that root is not a single number as it is with real numbers. The root is a solution to the equation epsilon to n equals z, where epsilon is what we look for, the root. It happens that every epsilon, being the solution, can be written as follows. Nth root of r, the root is our well-known root of a real number, times exponent I times phi plus 2k pi over n, where k is an arbitrary integer. We can check that our epsilon is indeed the root by taking it to the nth power. We make some operations on exponents, take into account periodicity of the angle, and we get it. Let k equals n plus m, such that m is smaller than n. Simplifying the expression shows that n does not influence the root. So instead of taking every integer, we can take k from the set from 0 to n minus 1. We denote this set as Zn. Looking at these roots, we can observe some interesting properties. Roots lie on the circle with the center at the origin. Additionally, they are evenly distributed on the circle. That is to say, the angle between 2 points for a given n is always the same. Do you remember the task? find all primitive nth roots of unity. Let's leave the word primitive for a moment. And we have nth roots of unity. And it simply means that our z is equal to 1. So what does it mean in complex numbers? We are 1 unit from the origin, so r equals 1, and the angle is 0, so phi equals 0. Our formulas are much more clear now. Entire set of the nth roots of the unity is denoted as En. We define a group as a set with some operation. Our group will be G with an operation asterisk. We say that our pair is a group when it satisfies 4 requirements. The first requirement tells us that when we take 2 elements of G and combine them, we will receive the elements still belonging to G. So, combining elements of G, we will not get out of G. The second one, we call it associativity, tells us that it doesn't matter in what order we perform operations. By that I mean something really precise, what's shown on the screen. We can't, for example, change the order of the elements in the equation, but what we can change is the order of performing operations within this equation. The third one is about the existence of a so-called identity element, which doesn't change the element it is taking the operation with. We often sign it as E. We call this element neutral element too. By the way, there can only be one identity element in a group. The fourth requirement tells us that for every element A in a group G exists a special element such that when we combine them two, we will get the neutral one. This special element is called the inverse, and for every A, the inverse element is unique. We commonly denote it as A2 minus 1, which is the inverse of A. Conversely, A is also the inverse of A2 minus 1. One of the easiest groups is the integers with addition. Indeed, when we add 2 integers, we get the integer. We know that it doesn't matter whether we add first and second integer and then the third one, or add the second and third, and this would be added to the first one. The neutral element is 0, and the inverse element to k is minus k, because adding them both gives 0. There's an interesting group, Zn set with addition modulo n. Zn set is a set of integers from 0 to n minus 1. When we add modulo n to numbers, it means first we add them and then get their remainder of division by n. Let's look at the example. Z8. We add modulo 8, 2 and 3. 2 plus 3 modulo 8 equals 5 modulo 8 equals 5. Now 5 plus modulo 8, 6. 5 plus 6 modulo 8 equals 11 modulo 8 equals 3. And so 3 is the answer. We would like to define what does it mean to take the power of elements. We say that a to k plus 1 is a to k asterisk a, where k is the integer. A to 0 is the group's neutral element. Now, when we have it, we can introduce generator's definition. We say A from group G is a generator of G if set of all integer powers of A is G. Using the generator, we can generate entire group. Look at group Z with addition. Let A equals 2. 2 to 0 is a neutral element, so it is 0. Then, using the definition, we get that 2 to 1 is 2, 2 squared is 4, 2 cubed is 6, and 2 to 4 is 8. Now, negative powers. 2 to minus 1 is minus 2, because minus 2 plus 2 is 0. Using this scheme, we get minus 4, minus 6, and minus 8. Overall, 2 generates all even numbers, so it is not a generator of Z group. In general, A generates a group containing all integers divisible by A, so 1 generates entire Z group and is the generator. Similarly, -1 is also the generator of our Z group. What about Zn group? For example, Z8. 2 gives us a set of itself, 4, 6, and 0. 2 is not a generator of Z8. Let's look at another example, 1. We get 1, 2, 3, 4, 5, 6, 7, and 0. Or, in other words, the entirety of Z8. Therefore, 1 is a generator of Z8. Now, let's consider 3. We have 3, 6, 1, 4, 7, 2, 5, and 0. It means all numbers from 0 to 7, so 3 generates Z8. As you can see, there's no obvious answer to the question what number is a generator. You may wonder, why are we talking about such things and how do they relate to complex numbers? The answer is, En sets are groups with multiplication. First of all, multiplication is an inner operation. When we multiply two roots together, we will see that it works. The second requirement was associativity. We write it down, use our knowledge about exponents, about Z group, and go back, and we get what we wanted. The third one was the existence of neutral element. If we remember that 1 is always one of the roots of unity, we immediately know the neutral element because 1 multiplied by any number gives this number. And the last one, inverse element. Multiplying epsilon k and epsilon l, we get 1. It gives us that 2 times k plus l has to be 0. So L equals minus k, but L and k were the indexes of the roots, and we do not have negative indexes. Thankfully, we can make a whole circle by adding n, and we get what we needed. To sum up this part, we have already proven that En set with multiplication is a group. By the way, entire set of complex numbers with addition is also a group, and the complex numbers without 0, this time with multiplication, is a group too. Now we are ready to fully understand the task. Nth roots of unity are complex roots of 1. Also, the word primitive stands for the generators of En group. So, what we are looking for are elements of En which taken to the next powers successively give us entire En set. For now, we know that not every element of a group is a generator. We will try to find out if there is any pattern to that. Managing roots of 1 with all their quite complicated notation is annoying. Hopefully, having done some algebraic transformations, we will get something more inviting. We have a problem with k plus m. But we know that in an exponent, we care only about angles from 0 to 2 pi, so k plus m over n must be smaller than 1. We can get it by adding k and m modulo n. Thanks to this, we will see that multiplying elements of En is the same as adding their indexes modulo n. Such similarity is called isomorphism. Now we can look at the example. Epsilon 2 cubed is in a sense the same as taking 2 to the power of 3 in Zn group. Epsilon 2 times epsilon 2 is epsilon 4, and epsilon 4 times epsilon 2 is epsilon 0. Likewise, 2 plus modulo 6 2 is 4, and 4 plus 2 modulo 6 is 0. It means that we can consider our problem in terms of Zn group instead of En group, which is much easier. Okay, finally we should start solving the task. Let's assume n is greater or equal to 2. Case when n equals 1 is boring, because En contains only one element, which is 1. Now we take k from Zn and ask whether k is Zn's generator. This time, let's take m from Zn. Then, raise k to the power of m, which translates to adding k to itself m times. Afterwards, calculate modulo n. In other words, it is k times m modulo n. It is important to notice that after reaching 0, we will get nothing new. In the current example, right after arriving at 0, we will get 2, and that's what we started with. If we continue, we will again get 4, 0, 2, 4, 0, and so on. So, what interests us is the first time we reach 0. This insight will be crucial to understand later parts of the reasoning. But what does it mean that we reach 0? It means that k to the power of m can be written as n times some integer L modulo n. We would like to check something. Is it true that if there exists a power b strictly smaller than n, for which k hits 0, then k does not generate Zn? Let's assume antecedent. It implies that number of elements in the generated group is smaller than number of elements in Zn group. Therefore, generated group cannot be Zn, and k is not a generator. Let's try to write left-hand side more transparently. We have that k to b is kb modulo n is 0, equivalently saying kb is a multiple of n. We denote it as kb equals ln. It means that kb is divisible by n. And because none of k and b equal n, then n and k have greatest common divisor greater than 1. But it's not the end. For now, we only have an implication in one direction, that is downwards. To be able to write what we had before in a new form, we need an implication upwards too. Then, we would have the equivalence. We have n and k not being relatively prime. Let's say that their greatest common divisor is d. If so, we can denote n as db and k as dA for some natural ab strictly smaller than n. In such situation, k to b is kb modulo n. We substitute k for dA from the third line and db for n from the second line. What we get is an modulo n, which evaluates to 0. So, we have just shown the implication we missed. Now, we can write down what we have, and see that the implication and the equivalence can be combined into the implication, which looks quite inviting. We would like to have similar implication with minor change. If greatest common divisor of n and k is 1, then k generates Zn. Let's use proof by contradiction. So now the implication changes to GCD of n and k is 1, and k does not generate Zn. If so, then there exists natural number a smaller than n, such that k to a is 0. That is, ak equals nl for some l. This means that ak is divisible by n, and because n and k do not have any common divisors different to 1, n divides a. However, we have already assumed that a is strictly smaller than n, so n cannot be its divisor. So we can conclude that our previous implication was true. In summary, we have proven these two implications, which led us to the answer. The final answer is epsilon k is a generator of En if and only if n and k are relatively prime.